Hi all. In the last video, we saw various systems in rotary drilling, like hoisting system, pressure control systems, mud circulation system, and etc. So, the fundamental concept behind that mud circulation system, which is an important system in rotary drilling, is drilling hydraulics. So, in order to have an efficient, safe, and cost-effective drilling project, proper drilling hydraulics has to be selected, and it plays a very important role. So if the drilling hydraulic design has not been properly done, then it leads to improper hole cleaning, and it leads to borehole problems like stuck pipe, lost circulations, and slow penetration rate. So some of the key concepts for the design of hydraulics, drilling hydraulics are maintaining a proper hydrostatic pressure, selecting the proper types of fluid flow like laminar or turbulent based on the scenarios, which we'll be discussing later, and also to choose based on the formation condition, geomechanical condition, to choose the proper fluid types. So coming to the concept of hydrostatic pressure, which is a very key concept for a single fluid column, there is not a much thing we know in elementary school that pressure at a particular depth will be equal to a rho gh. But if a fluid column has a multiple fluid, which is a complex fluid, uh, then the 4.1 applies, and because every for a certain depth have a different fluids, and if different fluids have a different density, and it has to be summated based on that particular amount of fluid occupies at a particular positions. So this is what it says about the equation 4.1. So rho mi is density or mud weight of a particular fluid column at a particular depth. In case of gas column, equation 4.2 applies, which involves like an empirical formula, exponential empirical formulas, which involves molecular weight, uh, temperature, and the depth at where the gas column is here, and it is a reference pressure or surface pressure, a reference depth, or a surface height. And it's a molecular weight formula. It's also an empirical formula 4.3. So for practical purposes, these are like various densities at various depths are being converted into an equivalent mud weight concept called ppg, which is expressed in equation 4.4. So it is related to the pressure at a particular depth, and it's also some kind of a formula based on the unitless conversions, dimensionless analysis. So this is equivalent to the mud weight to be always referenced to as a particular depth. For that particular depth d, this is going to be the equivalent mud weight based on the pressure at that particular depth, which again it's been computed through this concept of 4.1. So we have the concept of 4.1 equivalent mud weight. And in coming to the terms of annulus, we here one of the fundamental purpose of the drilling hydraulic is to transport the cuttings along the annulus, and so when fluid flow through the annulus, it also has multi-phase flows like solid, involved, suspended. So so to take into account, there can also be a gas formulated from the formations, and all these factors are considered into account to compute the average mud weight along the annulus, which is called as a mixture mud weight, which is equal to the summation rho a fi, and fi is a volume fraction of the particular fluid component. So if in case of density, if in case of a gas component is in particular pipe or from the annulus, so if that gas density will be a function of the pressure. If there is a more pressure, there will be a more gas density. So we all know that when the depth increases, the pressure increases. So indirectly, the gas density would be a function of the depth. If there is a the gas is trapped in a very deep depth, then then it will have high density. But if it is in a surface, then the density would be negligible. So for the deep section of the well, there will be a gas density will be very high, and it is a very negligible the density difference between this gas and the mud weight will be negligible. Then there will be hardly any variations, and those things are being ignored. And the average mud density along with the gas column is computed by equations 4.6. It is like a fraction of the gas column, and 1 minus Fg is a fraction of the fluid. But in case of shallow well, then it cannot be ignored, and there would be considerable difference in the density of the mud column and the density of the gas. In that aspect, equation 4.8 applies, which is nonlinear equations. And in that aspect, since it's a nonlinear equation, then it has to be solved through an iterative solver like Newton-Raphson method. So this paragraph is a very important paragraph. We can go the concept of one by one. So in order to have a safe drilling, so we need to maintain a particular pressure, hydrostatic pressure, such a way that it does not over exceed the formation pressure, and it as in such a way that it is not very far below the formation pressures. If it is far below the formation pressure, then there is a high chance that there will be a kick occur. The kick means there will be a flow of formation fluid into the borewell, and which eventually causes stability problem and collapse the borewell. But in case if it is a too high pressure, formation pressure, such a way that it can cause fracture in the formation, then the hydrostatic pressure greater than forming the fracture pressure will lead to formation of the pressures. So due to the leading to the formation of the pressure, then there will be a the fluid flow from the mud, the fluid from from the bore well will be flowing into the formation, which is eventually end up in a loss circulations. Which so for an effective drilling, we should not have a too high hydrostatic pressure, or it should not be too low pressure in comparison to the formation pressure. Too high pressure will lead to the loss circulation, too low will lead to the kick. So what in a conventional standardization would be always to maintain hydrostatic pressure a little higher than the formation pressure, a little bit over balance drilling, so that there so that the mud formed at the mud scale form will prevent either the kick or the fracture formation and end up in your loss circulations. But if it is if we are maintaining a too over balanced drilling, it end up in a poor efficient in cutting transport, or poor efficiency in maintaining the penetration rate of a PDC drill bit. So in that aspect, many drilling companies prefer to go for 100% drilling for an efficient penetration rate, using a very low density fluid like air, foam, and mist. So this can result in a constant kicking, and it has almost like a sensitivity in drilling operations. But people prefer for to have an efficient, quick drilling process. But in sensitive areas, these underbalanced drillings are usually prohibited by certain government norms. So hopefully we understood about telling what is the importance of maintaining the hydrostatic pressures to avoid either kick, uh, maintaining a very low pressure, or to avoid loss circulation, maintaining a pressure hydrostatic pressure higher than the fracture pressures. So hopefully we will come up with what are the different types of fluid in the next lecture. Thank you.